So I thought it might be quite good fun today to look at a technique for proving that your tests are actually testing what you think they are testing. Um, and that technique is called mutation testing. So in order to prove that our tests are testing what we think we're testing, we can go in and we can try and break the code and see if our tests also break at the same time. So let's give this a go. So I have here an implementation of the bowling kata. So the bowling kata, if you don't know, is a small kata where you give it the scores for a completed game of bowling, the scores every single roll, and it will tell you what the total scores for that game were. And there's a number of different kind of implementation details for this. So there's a thing like where it's a gutter game. There is a standard game where no one scores any special scores, where it just adds up all the scores. There is a spare, where someone scores a spare, and a spare is where you knock down all of the pins, but you knock them down in 2 rolls. And then there is the well-known one, which is the strike, which is where you knock down all the pins in a single roll. So what we can do is, if we think that we can have a look at our tests. So this is our test for our bowling kata game, and we can see that all of the cases are basically covered. But how do we know we've covered these in the right way? And how do we know that there's not any existing bugs in here? So a gutter game here is roll 20. So one thing that we could do to check that these tests are working is we could go into our code. We could go into our code and say, delete one of these lines. So if I delete one of these lines and then rerun the tests like I just have and have them pass, it means the tests aren't covering that particular case. And this is bad, obviously. We want our tests to cover our cases, all of our cases. But doing this individually for every single test case would be quite tedious. So really what we want to do is we want an automatic way of doing this. And this is what mutation testing is. So mutation testing does exactly what I just did, except it does it in an automatic way. So the mutation testing framework for PHP is called infection. So I'm just going to run it here. And what it's going to do is it's going to go through and try and break my code. So each of the M's is an instance where it's broken my code and my test didn't fail. So let's have a little bit of a look at what it did. So if I do cat and then infection.log, it'll output the change that it made which didn't fail. So in this instance, if we have a look at line 28, so we will find it took away this line, it changed it to a -1, and the test didn't fail. So we can do this and we can see that the test won't fail. So the tests don't fail. So what we need to do is we need to improve our tests so that we can catch this problem. So in this particular instance, the first block of this if here is scoring for strikes. The next bit of this if is scoring for spares, which is where you don't knock down all of the pins. And the final block of this if is scoring for just standard rolls by the looks of things. So we've got strikes, spares, standard rolls. And what we're doing here is we're saying, okay, so we've burned the first frame, we've burned the second frame, and then we're going to keep looping through the iteration. So we need to find the instance where we're testing a standard scoring. So if we have a look at it, what we're doing every single time is we're always just rolling one pin. And we're doing that 20 times. So we probably need to change this so that we're not always rolling the same pin, so that it has to, if it reads from a different place, it will cause the test to fail. So we can change this so we roll, let's roll the first one. The first one can be 2. And then we can roll 19 times 1. And that will be 21. So if I rerun the tests, check if they pass. Cool, so the tests still pass. And now let's rerun our mutation tests and see if we have fixed this problem. Oh, that was the wrong thing. I need to look at the logs. Yeah, okay, so we can see that we have actually changed the error which is coming up. We fixed one of those mutations which have escaped. So we know that we've improved our tests and we've made our tests better. So this is a really nice, simple little technique. And how this works in practice, in some systems this is very slow, and in some systems this is very fast. And this all depends whether the system has a fast in-memory system for executing code of itself. So how the PHP version works and how many of the fast versions work is what they do is they read this file here, this bowling kata, and they read it into something called an abstract syntax tree. Now an abstract syntax tree is a representation of this file but in code form. So we can actually have a little bit of a look at one of these. So these are what in the library for infection, so infection source, and then we can say the mutators. So these are the way it breaks our code to prove that it's working. We can find one of the instances where we are mutating the code. So this is an example of that. So what we do is we can see an instance of our abstract syntax tree here. So what we're doing is we're taking a Boolean OR and we're replacing an AND. We're taking a logical AND, and then instead we've been given the node, and then we're swapping it out for a Boolean OR. So we're mutating the code, and we're going to see if our tests fail every single time. Now, this repository is on our public GitHub, so I would really recommend checking it out. It is at Makuni/badbowlingkata, and it's in PHP, Java, and Python, so you can choose the language which you want to play with most. There is also a Ruby mutation testing thing, so if you want to add to this and create a Ruby version of this, that would also be very, very cool. So that's it for today, so thank you, I hope that was fun.